SpaceX just told investors that its rockets, satellites, artificial intelligence, and future industry beyond Earth could enable something far bigger than cheaper launches. The company used three extraordinary words: an age of abundance. That sounds like science fiction, or marketing, or both. But behind the phrase is a specific physical strategy: make transport to orbit radically more reusable, turn thousands of satellites into a global communications layer, use Starship to increase the mass and power delivered to space, build computing infrastructure where sunlight is plentiful, then extend production to the moon and eventually Mars. If even part of that stack works, SpaceX is no longer only selling rocket launches or internet subscriptions. It is trying to lower the price of connectivity, intelligence, energy, and access to physical resources at the same time. Today, we are going through the whole plan, from the businesses that already operate to the engineering that has not yet been proven. We will test the numbers, identify the bottlenecks, and ask the question that matters: is this really a path to abundance, or the most ambitious capital-intensive promise ever presented to public investors?
SpaceX. Investor. Not financial advice.
Before we begin, one distinction will keep this analysis honest. SpaceX is describing three different layers of reality. The first is operating now: Falcon reuse, Dragon missions, Starlink broadband, and the first generation of direct-to-cell. The second is a company expectation: Starship carrying commercial payloads, next-generation Starlink satellites, and an early orbital compute deployment on a stated timeline. The third is a long-range ambition: thousands of Starship launches, 1 million metric tons to orbit each year, 100 gigawatts of annual compute deployment, lunar manufacturing, asteroid mining, and cities on Mars. Those layers are connected, but they are not interchangeable. A design target is not a demonstrated capability. A possible market is not revenue. A technological breakthrough is not automatically affordable or evenly distributed. SpaceX itself warns that many of these systems are early, technically complex, capital-intensive, and may not become commercially viable. So we are not going to dismiss the vision simply because it is audacious, and we are not going to accept it simply because it appears in an offering document. We are going to examine the machine one layer at a time. This is SpaceX. Investor. The first scarcity SpaceX attacked was transportation. For most of the space age, a launch vehicle was treated like a custom object that destroyed itself while doing its job. That made every mission expensive, infrequent, and cautious. Reusability changes the economics because the most complex part of the system can fly again. But landing a booster is only the beginning. The real advantage comes from learning how to inspect, refurbish, schedule, and operate a fleet at industrial cadence. SpaceX says Falcon flew 165 missions in 2025. Its investor material also says the company has carried more than 80% of the world's mass to orbit since 2023. Whether a competitor can match one launch price matters less than whether it can match the entire operating system. Factories, pads, recovery ships, engines, flight software, regulatory practice, and the accumulated data from repeated reflights. Abundance begins when an exceptional event becomes routine infrastructure. Falcon did not make launch free, and it did not eliminate risk, but it compressed the cycle between manufacturing, flight, recovery, and flight again. That created the tempo required for everything else in SpaceX's strategy. The deeper breakthrough is not the rocket by itself. It is the feedback loop between a reusable rocket and a customer that needs launches constantly. In 2025, SpaceX says it delivered 2,213 metric tons to orbit. Only 312 tons belong to customers. About 1,901 tons were SpaceX payloads, overwhelmingly the kind of internal demand created by its own satellite networks. That changes the traditional launch business. SpaceX does not have to wait for the external market to produce enough missions to practice at high cadence. It can manufacture satellites, launch them on its own rockets, sell connectivity from them, and reinvest the cash and operational learning into more rockets and satellites. Each side of the company helps scale the other. This is why investors should think of launch abundance as throughput, not simply ticket price. The important variables are mass per flight, flights per year, turnaround time, reliability, and the amount of productive infrastructure created by every mission. Falcon established that flywheel. Starship is being designed to multiply it. But before we jump to the giant rocket, we have to understand the first product that transformed all of that launch capacity into recurring demand: Starlink. Starlink is the clearest example of SpaceX turning access to space into a service used on Earth. As of March 31st, 2026, the company's prospectus described a network of roughly 9,600 broadband and mobile satellites serving customers across 164 countries, territories, and other markets. Its 2025 progress report says it added more than 4.6 million active customers and expanded into 35 additional markets during that year alone. The important idea is not that satellites replace every fiber line or cellular tower. Dense cities are usually served more efficiently by terrestrial infrastructure. The advantage appears where distance, terrain, disaster, or low population density make conventional networks slow or uneconomic to build. A low Earth orbit constellation can distribute one shared infrastructure across ships, aircraft, farms, islands, remote communities, emergency teams, and moving vehicles. That makes bandwidth available in places where the alternative may be a weak connection or nothing at all. In the abundance thesis, connectivity is foundational. A school cannot use cloud tools without a network. A remote clinic cannot share data without a network. An autonomous machine cannot coordinate with a distant operator without a network. Starlink is not the end of abundance, but it can be the nervous system through which other capabilities travel. The scale of the remaining problem is easy to underestimate. The International Telecommunication Union estimated that about 6 billion people were online in 2025, roughly 74% of humanity. That still left 2.2 billion people offline. In low-income countries, only about 23% of the population use the internet. Coverage is only one barrier. Affordability, electricity, devices, digital skills, local content, and political conditions can keep people disconnected even when a signal exists. The same report showed that fifth-generation mobile coverage reached more than half of the world, but only 4% of people in low-income countries. So it would be misleading to say Starlink alone closes the digital divide. What it can do is remove part of the infrastructure constraint by delivering a backhaul or direct connection without waiting for a terrestrial network to reach every location. The economic test is whether service, terminals, power, and local distribution become affordable enough for the communities that need them most. Abundance of technical capability is not the same thing as abundance of access. That distinction will return later, because every layer of the SpaceX vision depends not just on what can be built, but on who can actually use it. Starlink also shows why vertical integration can produce a compounding advantage. A satellite operator normally buys a launch, leases ground infrastructure, purchases components, and depends on external schedules. SpaceX designs much of the satellite, launch vehicle, software, user terminal, ground network, and service together. When one part changes, engineers can optimize the rest. A heavier satellite may be acceptable if the rocket provides more capacity. A different orbit may be practical if launch cadence is high. A new terminal can be coordinated with network software and beam design. Inter-satellite laser links can route traffic through the constellation instead of relying entirely on nearby ground stations. None of that means the system is free from suppliers, regulation, or physical limits. It means the design space is larger because fewer interfaces belong to unrelated companies. The investor case is that this integration reduces iteration time and lets SpaceX move savings or performance from one layer into another. The risk is concentration. The same company controls access, infrastructure, prioritization, and increasingly the services traveling through the network. An abundance engine can also become a gatekeeper. The architecture creates efficiency, but the rules governing that architecture will determine whether the resulting power is broadly competitive or tightly controlled. The next step is to make satellite connectivity disappear into a device people already carry. Starlink's first direct-to-cell generation is designed to connect ordinary compatible phones through partner mobile networks without a special satellite handset. SpaceX says it deployed more than 650 direct-to-cell satellites in 18 months, and that the service connected more than 12 million people at least once by the end of 2025. The report describes messaging, location tools, social applications, weather information, and early data service across more than 30 applications and 100 optimized devices. This matters because the most valuable connection may not be the fastest connection. It may be the first signal after a hurricane, the map that loads beyond terrestrial coverage, the message from a stranded traveler, or a sensor reporting from a remote field. The satellite effectively acts like a cell tower moving through space. Partner carriers supply spectrum and customer relationships, while the constellation supplies reach. In abundance terms, direct-to-cell attacks the dead zone, the places where a person has a functioning phone but no local network. The ambition is not unlimited broadband everywhere today. It is a minimum layer of communication that follows the user beyond the edge of terrestrial coverage. Direct-to-cell also exposes the difference between a compelling demonstration and a mature capacity layer. A satellite beam is shared. Spectrum is limited. Trees, buildings, terrain, device orientation, network congestion, and national regulation all affect performance. A few text messages during an emergency require far less capacity than millions of people streaming video. SpaceX's next-generation mobile satellites are intended to provide more comprehensive broadband and Internet of Things service. And the prospectus says the company expects Starship deployment beginning in 2027. That expectation depends on the rocket, the satellites, partner spectrum, approvals, and devices all arriving together. Still, the strategic direction is clear. Starlink broadband connects a terminal. Direct-to-cell connects the phone itself. Internet of Things service connects machines that may be too remote for a normal tower. When people, vehicles, farms, ships, and autonomous equipment can all exchange data, connectivity becomes less like a product and more like an ambient utility. The question is, how much useful capacity the system can deliver at a sustainable cost? That brings us to the vehicle intended to change the numerator in almost every SpaceX equation. Starship. Falcon made reuse operational. Starship is attempting to make the entire launch vehicle rapidly reusable while increasing payload volume by an order of magnitude. SpaceX says Starship version 3 is designed to carry 100 metric tons to orbit in a fully reusable configuration. A future version 4 could reach 200 metric tons. Those are design figures, not a guarantee of operational payload or cadence. But the reason they matter is simple. Most space systems are designed around scarcity. Engineers minimize every kilogram because launch is expensive and fairing volume is limited. If mass and volume become more available, designers can trade some extreme optimization for redundancy, shielding, larger power systems, easier manufacturing, or faster iteration. A satellite could carry bigger radiators. A telescope could launch with fewer complex deployment mechanisms. A lunar cargo mission could move construction equipment instead of a small science package. The effect would not be that engineering becomes easy. It would be that a different set of solutions becomes economical. SpaceX expects Starship to begin payload delivery in the second half of 2026. Until that happens reliably, the abundance story remains anchored to Falcon. The decisive transition is not the first payload. It is repeatable payload delivery, recovery, inspection, and reflight at a cadence customers can plan around. Next-generation Starlink makes the throughput argument concrete. SpaceX says one Starship could carry as many as 60 version 3 broadband satellites. Each is designed for roughly 1 terabit per second of downlink capacity. Together, one launch could add about 61 terabits per second, more than 20 times the downlink capacity added by a current Falcon launch carrying version 2 satellites. Again, designed capacity is not the same as real-world customer throughput. Ground demand, spectrum, gateway placement, interference, network software, and satellite availability all matter. But a 20-fold increase per launch explains why Starship is not merely a Mars project. It is central to the economics of SpaceX's existing network. More capacity can support more customers, higher usage, enterprise service, mobile coverage, and lower cost per delivered bit if demand and operations scale with it. The same launch vehicle can also carry larger mobile satellites and future compute platforms. This is the core abundance flywheel. A bigger reusable vehicle puts more productive equipment in orbit. That equipment generates service revenue or strategic capacity, and those returns fund the vehicle and infrastructure that launch the next generation. The outcome depends on whether the rocket flies often enough for the spreadsheet to become a physical operating system. Cadence is where the vision becomes both most powerful and most vulnerable. SpaceX discusses multiple launches per day as a design goal, and in its most ambitious scenario, thousands of launches per year. That would require vehicles, engines, propellant production, pads, towers, airspace coordination, environmental approval, recovery zones, and maintenance systems operating with a rhythm closer to aviation than traditional rocketry. Deep space missions add another requirement: transferring large quantities of cryogenic propellant in orbit. SpaceX tells investors that in-orbit refueling is essential for its lunar, Mars, asteroid mining, and other deep space ambitions. The company also disclosed that it had not yet attempted or demonstrated the capability at the filing date. Propellant must be launched, stored with limited boil-off, transferred between moving vehicles, and managed safely in microgravity. A lunar landing architecture may require a campaign of tanker flights before the lander departs Earth orbit. Each additional flight introduces schedule and reliability dependencies. This does not make the architecture impossible. It makes the true product larger than Starship. The product is a high-cadence orbital logistics network. Until that network exists, 100 tons to orbit is a vehicle specification. After it exists, it could become the freight layer for an off-world economy. Now we reach the most controversial part of the strategy: putting large-scale artificial intelligence computing infrastructure in orbit. SpaceX argues that the artificial intelligence economy is constrained by power, data center construction, land, cooling, and grid interconnection. A solar-powered satellite has access to strong sunlight for much of its orbit and does not wait years for a terrestrial transmission line. Starlink already provides a manufacturing base, flight heritage, laser networking, and a global communications architecture. The prospectus says SpaceX could begin deploying Orbital AI compute satellites as early as 2028. Early is the important word. These would not simply be Starlink satellites with a different software package. The company says they need much larger solar arrays, much larger radiators, and electronics centered on compute accelerators rather than communications payloads. Its initial design analysis targets roughly 100 kilowatts of compute power per metric ton. The grand ambition is to deploy up to 100 gigawatts of new capacity each year. That number is not a forecast of near-term operation. It is the outer edge of a system that would require thousands of launches, enormous satellite production, and a market willing to buy the output. The credible starting question is smaller. Can useful computing workloads operate economically in orbit at all? Space does offer a compelling energy resource, but the phrase unlimited solar power can hide the engineering. A platform in low Earth orbit moves rapidly between lighting conditions, unless its orbit and storage system are designed around the duty cycle. Solar arrays must survive radiation, thermal cycling, micrometeoroids, vibration, and launch loads. Power electronics must distribute energy to accelerators that generate intense heat. Batteries or workload scheduling must handle eclipse periods. The whole platform must control attitude while presenting large surfaces to the sun and radiators to cold space. The potential advantage is that the energy source arrives without fuel, and the system can be expanded by launching more modules. The potential disadvantage is that every failed component is hundreds of kilometers above the repair technician. A terrestrial data center can replace a pump, add a transformer, or swap a server rack. An orbital platform needs extraordinary redundancy, robotic servicing, modular replacement, or a willingness to deorbit failed equipment. The abundance thesis works only if manufacturing and launch costs fall faster than space hardening and maintenance costs rise. Solar energy is plentiful in orbit. Reliable, dispatchable, serviceable compute is not automatically plentiful. The difference between those two statements is the entire engineering program. Heat is the constraint that gives orbital compute its reality check. On Earth, data centers can move heat into air or water. In vacuum, there is no surrounding fluid to carry heat away. The system has to radiate energy as infrared light, which requires large surfaces and careful temperature management. The more compute power concentrated in one platform, the more radiator area and mass the architecture may need. Radiation can also corrupt memory, degrade electronics, and shorten component life. Then comes networking. Training a frontier model requires accelerators to exchange enormous amounts of data with low latency and high reliability. SpaceX already operates tens of thousands of inter-satellite laser links across Starlink, but communication satellites routing internet traffic are not the same as tightly coupled accelerator clusters. Some orbital workloads may be better suited to inference, pre-processing Earth observation data, or tasks that can tolerate delay. Others may require data to move to and from terrestrial users, reducing the value of placing the compute in space. The correct investor question is not whether computers can operate in orbit. They already do. It is which workloads earn more money or avoid more cost in orbit than on Earth after launch, replacement, networking, and thermal management are included. This is why SpaceX presents orbital compute as a ladder instead of one giant leap. A modest deployment can test power, thermal performance, networking, component survival, and commercial demand. The company says a 10-gigawatt annual deployment rate would require materially less manufacturing and launch cadence than its 100-gigawatt ambition and could still support an attractive business. Even 10 gigawatts would be enormous by space industry standards, so the word modest is relative. The strategic advantage SpaceX claims is control of the physical stack: chips, satellites, lasers, software, launch, and artificial intelligence services. If one company designs the accelerator package and the spacecraft around each other, it may reduce mass and communication overhead. If Starship carries 100 tons repeatedly, it may replace failed modules faster and at lower cost. If the laser mesh routes data without touching the ground at every hop, the constellation may act like a distributed data center. But every if has to become a measured result. Watch for kilowatts deployed per satellite, useful accelerator performance, radiator mass, lifetime, failure rates, network utilization, customer contracts, and the cost to replace a unit. Abundance becomes credible through unit economics, not through the size of the ultimate diagram. The Moon enters this strategy for a different reason. Orbit can provide location, sunlight, and network reach. The Moon can provide a surface, local materials, and a staging ground beyond Earth's atmosphere. NASA is working with SpaceX to develop Starship Human Landing System for Artemis 3 and Artemis 4. NASA describes the lunar version as about 165 feet tall, roughly a 15-story building, with an elevator to move crew and cargo between the vehicle and the surface. If Starship can land large payloads repeatedly, the character of lunar missions changes. Instead of packing every experiment into a small robotic lander, missions could deliver power systems, pressurized habitats, rovers, excavation equipment, communications, spare parts, and eventually manufacturing tools. But the schedule is under pressure. NASA's Inspector General reported in March 2026 that lander development challenges would delay planned Artemis dates. Starship HLS also depends on the orbital refueling campaign we discussed earlier. The Moon therefore serves as both destination and test. It is where SpaceX must prove that its high-throughput transport system can operate beyond Earth orbit, land safely, support people, and return them. A lunar economy begins with logistics, not mining revenue. A functioning lunar supply chain could create several markets before anyone exports a valuable resource to Earth. Governments and research institutions may pay for cargo delivery, communications, navigation, power, mobility, construction, and scientific access. Private operators may sell surface services to multiple missions instead of every customer building a separate system. A landing pad used repeatedly is infrastructure. A power station serving several habitats is infrastructure. A communications relay, a pressurized workshop, or a fleet of autonomous haulers can become shared capacity. This is the same transition Falcon demonstrated. Move from isolated missions toward a network with recurring use. SpaceX's filing describes repeatable cargo and crew transport, energy production, and manufacturing on the Moon as elements of a future lunar economy. Those are long-range ambitions. They require enough customers, legal clarity, interoperability, safety standards, and dependable transport to support investment. The first lunar businesses may look less like a gold rush and more like ports, utilities, and logistics contractors. The investor opportunity is not necessarily a rare material brought back to Earth. It may be lowering the operating cost for every mission that follows. If the cost of moving equipment to the lunar surface falls, more activities become possible. If activity grows, infrastructure is used more often. That is the abundance flywheel in a new environment. Local resources could eventually reduce the mass that must be launched from Earth. NASA is developing in-situ resource utilization technologies for extracting and processing materials already present on the Moon. Water ice, if available in useful concentration and accessible form, could support drinking water, oxygen, and hydrogen. Oxygen can also be bound inside lunar minerals. Regolith may become feedstock for landing pads, berms, roads, shielding, or construction. The attraction is obvious. Every kilogram produced locally is a kilogram that may not need to climb out of Earth's gravity well. But resource abundance in a map or soil sample is not economic abundance. Engineers need to locate deposits, excavate in extreme cold or abrasive dust, separate useful material, supply continuous power, maintain machinery, and store the product. NASA explicitly notes knowledge gaps in the location, concentration, distribution, and extraction of lunar resources. A deposit can be scientifically real and commercially useless if it is too diffuse, too deep, or too expensive to process. The honest timeline begins with prospecting and demonstration plants, not industrial exports. The Moon becomes economically transformative only when local production costs less, improves safety, or enables missions that Earth-supplied logistics cannot support. Until then, in-situ resource utilization is a promising experiment, not a commodity market. A hidden requirement across the entire abundance thesis is autonomy. Thousands of satellites cannot be managed one by one. A high-cadence launch system cannot depend on handcrafted decisions at every step. Orbital compute platforms cannot wait for astronauts to replace every failed component. Lunar mines and power stations will operate far from supply chains, and in some cases, through long periods of darkness or communication delay. The system needs machines that inspect, diagnose, schedule, route, repair, and adapt. Artificial intelligence is therefore not only a product SpaceX wants to sell, it is an operating technology for the infrastructure itself. A launch site can use automated inspection. A constellation can route around failures. A lunar hauler can navigate terrain. A factory can adjust production based on launch demand. This creates another feedback loop. More infrastructure generates more operational data. Better models use that data to improve reliability and autonomy. Improved autonomy allows more infrastructure to operate with the same human team. The danger is that software errors can also scale. A flawed update, cyber attack, sensor failure, or optimization target may affect an entire fleet. Abundance through autonomy requires graceful degradation, independent safety systems, human override, and an engineering culture that treats rare failure modes as inevitable rather than impossible. Now the entire SpaceX map can be seen as one compounding machine. Reusable rockets increase launch cadence. Launch cadence lowers the cost and schedule risk of deploying satellites. Satellite networks generate connectivity revenue, global reach, and operational data. Starship increases the mass, volume, and power available per mission. That capacity supports larger communication satellites, mobile coverage, orbital compute, and lunar cargo. Artificial intelligence improves the design and operation of factories, networks, vehicles, and robots. Lunar resources, if they become practical, reduce dependence on material lifted from Earth for activity beyond Earth. Each layer can create demand for the layer below it, and capability for the layer above it. This is why SpaceX believes vertical integration is more than a manufacturing preference. The company is attempting to coordinate transport, energy, compute, communications, and automation as one system. The advantage is speed of iteration and the ability to optimize across boundaries. The risk is that weakness in one critical layer propagates through the whole stack. If Starship cadence stalls, next-generation satellites and compute deployment slow. If regulation constrains spectrum or launches, network growth changes. If orbital compute lacks compelling economics, a major demand pillar disappears. Compounding works in both directions. A flywheel accelerates success, but tightly coupled dependencies can also accelerate disappointment. Any serious age of abundance analysis has to count the external costs as carefully as the internal efficiencies. Thousands of launches affect communities, airspace, coastlines, wildlife, and the atmosphere. Large constellations increase collision management responsibilities, re-entry traffic, radio interference, and effects on astronomy. Lunar operations raise questions about contamination, heritage sites, shared resources, and the rules governing commercial activity. Orbital compute adds huge structures, replacement cycles, and potentially large quantities of hardware that must be deorbited safely. Regulation is not merely paperwork standing between engineers and progress. It is the mechanism through which a private system negotiates with public safety, environmental limits, national security, and other users of shared domains. Poorly designed regulation can freeze innovation. Weak regulation can socialize risks while concentrating benefits. SpaceX's ability to scale will depend on earning durable permission, not just receiving individual launch licenses. That means transparent environmental data, verifiable debris mitigation, reliable disposal, coordination with astronomers and spectrum users, and infrastructure that can fail without creating cascading hazards. True abundance cannot be measured only by how much hardware reaches orbit. It also has to include whether the surrounding environment remains usable for the next operator, the next nation, and the next generation. There is also a political and economic question hidden inside the word abundance. A society can produce more energy, bandwidth, compute, and material, while many people remain unable to afford them. The digital divide proves that coverage and adoption are not the same. Artificial intelligence can increase productivity, while gains flow mainly to the owners of infrastructure. A lunar economy can expand human capability, while access remains limited to a few governments and corporations. SpaceX may lower the physical cost of important services, but prices, competition, public investment, labor markets, and policy determine how those savings reach ordinary people. This does not weaken the technology thesis. It defines the work required after the technology succeeds. Cheap launch can support more science if research institutions can purchase missions. Satellite coverage can support rural education if communities have terminals, power, devices, and training. Abundant compute can accelerate medicine or engineering if researchers and small businesses can access it. The most optimistic SpaceX vision is not simply more machines in more places. It is a larger frontier of choices for people on Earth and beyond it. The investor should therefore watch both cost curves and market structure. Capability creates the possibility of abundance. Distribution turns that possibility into a lived economic condition. For investors, the abundance thesis needs a scoreboard that cannot be satisfied by one spectacular launch. Start with Starship payload delivery. Measure useful payload to orbit, vehicle recovery, refurbishment work, turnaround time, and flights per vehicle. Then measure the network. Version 3 satellites deployed, capacity activated, customer growth, revenue per delivered bit, terminal cost, and the performance of direct-to-cell under real congestion. For orbital compute, ignore the most dramatic gigawatt target at first. Watch the demonstrator: kilowatts in operation, accelerator utilization, thermal margin, data moved through the laser network, component lifetime, and signed customers. For the moon, count completed propellant transfer tests, tanker flights, uncrewed landing milestones, cargo mass delivered, surface operating days, and the first resource product measured in kilograms rather than presentation slides. Finally, track capital efficiency. How much investment is required before each new layer produces cash or strategic capability? A vertically integrated system can hide weak unit economics because one division supplies another. The right analysis separates transfer activity from outside demand and asks whether every layer becomes more productive over time. The abundance story deserves long-term thinking, but long-term thinking still needs near-term evidence. A credible vision should generate a sequence of increasingly difficult, independently verifiable results. So, is SpaceX building an age of abundance? The operating evidence says it has already made launch more reusable and orbital connectivity more available. It has also assembled a uniquely integrated route from factory to orbit to service. That makes the vision more credible than a concept proposed by a company that owns none of the required infrastructure. But the largest claims still depend on capabilities that are unfinished, unproven at scale, or not yet attempted. Starship must deliver and refly with dependable cadence. Propellant must move between vehicles in orbit. Compute platforms must reject heat, survive radiation, and produce value that customers will pay for. Lunar machines must operate through dust, darkness, and distance. Regulators and communities must permit the system to scale, and lower physical cost must become affordable access instead of concentrated control. My verdict is neither blind optimism nor dismissal. SpaceX has assembled the most credible physical stack yet proposed for expanding humanity's access to orbit, networks, energy, intelligence, and off-world industry. That is already historically important. Yet abundance is not a phrase in an offering document or a single launch milestone. It is a sustained decline in cost, a sustained increase in useful access, and an infrastructure system safe and resilient enough to keep operating. We will follow every proof point. Subscribe. This is SpaceX Investor.